So going through these questions, we're going to do one at a time and explain some of the knowledge behind each one to help you understand them. So here we're told we need to work out the number of protons, neutrons, electrons for an aluminium ion. If we remind ourselves, from the information that we have been given, the mass of aluminium is 27 and the atomic number is 13. So because the atomic number is 13, that means it has 13 protons. Neutrons, you do top number, take away bottom number, is 14. Now electrons, be careful because this is an ion. As you can see, it's got a charge. So what I suggest you do is use it as an atom and then change it to an ion. Remember, ion just means charged particle. So as an atom, it would have 13 electrons and they would be arranged as 2, 8, 3. But the 3 in the outer energy level means it's not stable. So it would lose those 3 electrons to become 2, 8, which is stable. When you lose electrons, electrons are negative, so you become positive. And because you lose 3, you become 3 plus. And therefore, you've got 2 and 8, 10 electrons left. So here, you're getting 1 mark for each of your answers. Okay, silicon has this configuration. Can you work out which period and group it's in? So first thing to do here is the 4 is the group number. So number of electrons in the outer energy is the group number. And then the fact there are 1, 2, 3 energy levels, that tells me it's in the third period. So here it's in period 3 and it's in group 4. And again, we're getting 1 mark for each answer. Okay, draw a diagram, outer electrons only, showing the bonding in carbon dioxide. Let's use everything here to help us. So first of all, dioxide means it's 2 oxygens. So the word di means 2. So I'm looking to have a formula that is CO2, therefore it's 2 oxygens. Next thing, carbon has got 6 electrons, so we would arrange those as 2, 4. And oxygen has got 8, and I'd arrange those as 2, 6. It wants me to only draw the outer electrons, so I'm only going to draw the 4 and the 6, which is what I've prepared here as my atoms. Let me take the carbon, and let's just move that over here to a bit of space, okay? So there's my carbon. Now, what we should remember here is that these two elements are non-metals, and because they are non-metals, we are looking at covalent bonding, and covalent bonding is sharing pair of electrons, so sharing a pair of electrons. So let's bring my oxygen over. So let's do that and bring that across as well. And I'm going to overlap the energy levels like so. Okay, right. First thing I'm going to do is we're going to share this electron here. Let's just move that for a minute. And it's going to share that electron by putting it in here. Now, if it shares that one, oxygen has to share one as well. So let's remove one of the oxygen electrons. Let's get rid of this one here. Right, and if we just check and count, oxygen has got a share of 1, 2, 3, 4, 5, 6, 7. That's not enough. It needs to have a share of 8. So what oxygen is going to do is oxygen is going to put another electron in. So there is another electron. But if it puts one in, carbon also has to put one in. So let's remove one of carbons. It's gone. And let's now count these. So 1, 2, 3, 4, 5, 6, 7, 8. So that means that oxygen is stable. But the carbon, 1, 2, 3, 4, 5, has only got 6, so it's not stable. So what I'm going to do here is bring the second oxygen over. because remember it's carbon dioxide, 2 oxygens. I'm going to drop that into there. And I'm going to replicate, copy exactly the same structure. Let's get rid of that. I'm going to get rid of that for a minute. So there's 2 electrons from carbon. 1, 2. You saw me rub out 2 electrons from. Oh, hang on. What's the? Keep jumping down there for some reason. You saw me rub out 2 electrons from the oxygen. So let's put those in. 1, 2. And you can see now, if I just count the carbon, because it was the carbon initially that wasn't stable. 1, 2, 3, 4, 5, 6, 7, 8. So this carbon's got 8. This oxygen's got 1, 2, 3, 4, 5, 6, 7, 8. So that's got 8. So that's stable. So that's my molecule of carbon dioxide. And if we look inside here, you can see there are 2 electrons there being shared, and there are 2 electrons there being shared. So we've actually got here, carbon has got 1, 2 covalent bonds to the oxygen, and this side's got 1, 2 covalent bonds to the oxygen as well. So that's what it would look like as a molecule. Okay, we're then told that carbon dioxide has a boiling point of -78, which is low. So when I see this in my head, this is the image I have got. So my image is, there's my carbon dioxide molecules, we've just drawn it. And I've drawn a second one here. But between the 2 molecules, we have got weak forces between the molecules. Inside the molecules, these covalent bonds are strong. So because my melting and boiling point is very low, something here is weak and easy to break, and it's these forces that I break. So my answer needs to really explain that. So there are weak forces of attraction between the molecules, and they do not need a lot of energy to break. So I'm not breaking bonds, but I'm breaking forces. In an exam, stating that gets you a mark, and then explaining that it doesn't need a lot of energy gets you a second mark. Just jump back up here one step, because I'm not sure. You've got 2 marks here. So you normally get a mark for showing the bonding electrons. So you get a mark here to show the bonds. And then you get another mark for any other electrons. Okay. Right. Diagram below shows silicon dioxide. Identify the type of bonding present and explain why it has a melting point of this. Okay, so this structure, hopefully you are recognizing a similar structure to this one. And this one you should recognize as graphite. And graphite is a giant molecular covalent substance. Okay, so our knowledge is going to be based on this understanding. So here we say it's got a giant molecular covalent structure. This means it contains lots and lots of covalent bonds. So all these lines in between them are the covalent bonds. So it contains lots of strong covalent bonds. And because there's lots of them and they're strong, these require a lot of energy to break. And that's why it's so high. Okay, so solid copper sulfate can't conduct. So this is why solid can't conduct. So solid copper sulfate is an ionic compound. So you've got positive, negative ions. But when it's in a solid state, all the ions are bonded to each other. And therefore these ions cannot move. If I put my copper sulfate into a solution, then the lattice is broken, so these bonds are broken, and the ions are free to move. So for example, this ion is able to move about over here, and this ion can move over here, and this ion can move over there. So the ions are free to move because the bonds are broken, and therefore it will conduct. So to get my 2 marks, I need to say that in the solid, the ions are not free to move, but in the solution, the bonds are broken, so the ions are free to move. Okay, calculation. Here I've written down two triangles. You need to know these triangles. You're not going to be given these triangles in the exam. And this question, this is a tough question. This would be a higher paper question. And you need to use both of these triangles in your answer. First bit of advice for you. Whenever they give us a mass in grams, we always have to convert it to moles. So I'm using this triangle here, and it says moles is the mass divided by the MR. So my first job over here is to work out the moles. I'm going to write down the moles is mass divided by MR. So the mass of this is 31.9. Okay. The MR, I'm going to go up here and we're going to work this out. So in my formula, we have got 63.5. So I've got 63.5 plus, I've got sulfur whose mass is 32. So plus 32 plus oxygen is 16, but I've got 4 of them. So I've got 4 times 16. Okay, I'm just going to plug that into my calculator. So I've got 63.5 plus 32 plus 4 times 16, and that's giving me an answer of 159.5. So here my MR is 159.5. So let's do this calculation now. So 31.9 divided by 159.5 is 0.2 moles. Now if I get that far, I'm going to get myself a mark for working out the moles. So if you do nothing else, you've got one of the marks for this question. So it now wants me to calculate the number of atoms. So I'm going to use the second triangle, because the second triangle, if I want to work out the number of particles, in this case they're atoms, I do moles times Avogadro's constant. So here, let's do the number of atoms equals moles times Avogadro's constant. So the moles we've just worked out 0.2. Avogadro's constant, we're told here, is 6.02 times 10 to the power of 23. So let's times that and do that calculation. So here I'm getting an answer of 1.204 times 10 to the power of 23, and that's the atoms. Now again, if I've got that far, I'm going to get myself another mark. Let's divide this page up a little bit. I've got one more step to do. The final step is the one that most people forget, so let's not fall into that trap. That is how many atoms there are in 1 mole of this stuff, but we've got to remember that every mole contains more than one atom. So what I mean by that is a mole of copper sulfate, but in this copper sulfate we've got 1 mole of copper atoms, we've got 1 mole of sulfur atoms, and we've got 4 moles of oxygen atoms. So my total is 4 plus 1 plus 1 is 6 moles of atoms. So all I need to do now to work out the total is take that 6 and times it by how many atoms I worked out that I had. So times that by 6 and you get 7.224 times by 10 to the 23 atoms. If I do that, that gets me my final mark. As I said, that's a really hard question. Wouldn't appear on a foundation paper, but does appear on a high paper. But everybody must be able to get this far and potentially this far. Okay, next question is against a reacting mass question. So we're using this triangle again. You can see why this triangle is so important. And what I'm going to do, I'm going to do this as a table format. Okay, so in experiment, we've got chlorine reacting with copper to make copper chloride. So I'm interested in the chlorine because we told we've got 15 of that, and I'm interested in working out the mass of the copper chloride. So we're interested in those two. And let's do some working out. Okay, so we do A first. So here I'm going to write down the chlorine, Cl2. Then I'm going to put the copper chloride here. And the first thing I'm going to write down is the mass. So the mass of chlorine is 15. Then I'm going to do the MR. So chlorine, there's 2 chlorines in there, and 1 chlorine is 35.5. So 2 chlorines is 71. I then need to work out the moles. So according to my triangle, the moles is the mass divided by MR. So it's mass divided by this. So it's 15 divided by 71. And let's just put my answer here. So I'm getting 0.211. And then the next thing I'm going to do is the ratio from the question. So you can see in this one, I've got 1 mole of this making 1 mole of this. So here I'm just going to put 1. And then let me just divide this so we don't get ourselves confused. And on this side, I'm going to put 1. Okay. So if the ratio is 1 to 1, then I'm going to have exactly the same number of moles. So if I had 0.211 here, I've got 0.211 here. Okay. The MR, we can work the MR out. So I'll work the MR up here. So here you've got 1 copper, which is 63.5. We've got 2 chlorines, which is 71. Add those together, 63.5 plus 71, and I'm getting 134.5. So 134.5. And then all I have to do, I want to work out the mass. Oh, keep pressing on the button there. I want to work out the mass. So my mass, according to this, is MR times moles. So it's MR times moles. So times that by 0.211. Okay, and we're getting an answer here of 28.4. Let's just check. It tells me it should make 41.62. That's not making the right amount. So this one, it's not reaction A. Let's just check and make sure it's definitely reaction B. So over here, let's do this for reaction B. And what I'm going to do, I'm going to cheat a little bit. I'm going to copy that, and then you can see exactly, paste it over here. You can see exactly what it is we're going to do. Let's just tidy that top bit up there, 3 cells. So this needs to be B. Right. Just check a couple of things. So first of all, in this equation, you can see here that we're actually making copper chloride and it's got a different formula. So let's change that because that's going to change my mass. Get rid of that, get rid of that, get rid of that, and get rid of these two. So the first bit of this working out is exactly the same. We have 15 grams of chlorine. Chlorine is 71, and that means there's this many moles. The ratio of chlorine is still 1, so let's put that in. But this time, the ratio of copper chloride is 2. So here, I'm putting 2. So now I've got 0.211 times that by 2, and here I'm getting 0.422. The MR, let's work the MR out. So copper is 63.5, chlorine is 35.5. So I've got 63.5 plus 35.5 equals 99. So in there, I'm going to put 99. That's not right. Let's just work that out. What's my calculator done? 63.5, is it right? Plus 35.5 is 99. Didn't seem right to me. 99. So all I need to do now is work out the mass. Remember, to work out the mass, we do mR times moles. So I've got 0.422 times 99, and that's going to give me 41.78. It's a little bit different to this because down here we rounded things up, but this one therefore is the correct one. So B is correct, A is not correct. Okay, carrying on, last couple. What's the name of the apparatus? So this process here is called fractional distillation. And then it wants us to label some bits. So the thermometer and the beaker wanted labeled, and it wants us to show us how the water moves through the condenser. So the water comes in to the bottom part of the condenser, as you can see here, and the water then flows out at the top part of the condenser. And this is just to keep everything cool so that it will condense, because the hot gases come in here and they're going to condense and turn back into liquids and then be collected in the beaker. So 1 mark for each of the labels in there. What does this mean? This here means this is corrosive for 1 mark. And then we had to plot a pH curve. So here we've got the data. So we need to plot these values on this graph, which I've actually done in preparation. I'm going to zoom out a little tiny bit. So we've got that ready. As you can see here, this graph is this kind of S shape. So when you get 1 mark here, if you plot the points correctly, I get a 2nd mark if I draw the best fit. Now remember, rule for best fit is you want to pass through as many points as possible, but this graph has to be that S shape that we just did. So here it's nice and flat, then it curls up. Oh, that's unfortunately wants to turn it into a straight line. Then it curls up, and then it comes off like this, okay? So that's what it needs to look like. If you do best fit and you do stuff like this, where then you have lots of like lines drawn in it, this is not going to get you marks because these points here are too thick. So your line of best fit, when you draw it, has to be just a nice smooth line without any of these little lumps and bumps in it. Okay, so 1 mark for the line, 1 mark for that. Use the graph to work out what happens when 3.5 spatulas are added. So to do this, what I'm going to do is come to the point here where 3.5 is there. Okay, what I'm then going to do, if this will let me, is draw a line up to the point where 3.5 hits this, and then take it across, and you can see I've got 8. Okay, so here I need to have 8 spatulas added. Right, explain why the pH starts off low and ends up high. So at the beginning, this solution contains hydrogen ions, and the core knowledge you need to know is if acids have a low pH because they contain hydrogen ions. So to do this, I'm going to do this in stages. I'm going to say at the start, the solution only contains hydrogen ions. And this means that the pH is low. Alkalis, they contain hydroxide ions. So again, my chronology is alkalis, they want to have a high pH, and they contain hydroxide ions. So the second step in my answer is that hydroxide ions are added and they neutralize the H plus ions. So the pH increases. And you could also, if you want to show off, you could say at pH 7, your hydrogen ions equal your hydroxide ions. So the number of hydrogen ions equals the hydroxide ions. And then the final bit, at the end, all the H plus ions have reacted. There are extra or there are excess OH minus ions. So the pH is high. Okay. Each points I put in there, so 1, 2, 3 is worth a mark. Last couple, during reaction, change from 2 to 3. What happens to hydrogen ions? So again, your core knowledge here is you should know that a pH change of 1 means a change in 10 for hydrogen ions. So if I'm going from pH 2, let's say I'm going from 1 to 3, sorry, so I'm going from pH 1, so my pH is 1, then it's going to go to 2, and then it's going to go to 3. What I've done here is my hydrogen ions, to get from there to there, have increased by 10, and to get from there to there, also increased by 10. So they've increased by a total of 100, and that's my final answer. So the hydrogen ions change by 100. 2 marks. I think you get 1 mark for showing the kind of logic, and then 1 mark for giving your answer. Right, test for hydrogen. Please make sure here you describe the test. Don't just say pot test. So what you do is you place a lit splint into the gas, and if it's hydrogen, it will burn with a squeaky pop. So you get 1 mark for each answer. And then the last one, write a half equation for what happens to hydrogen ions. So hydrogen ions are positive, and what we're trying to turn it into is just hydrogen. So what I'm going to do is add an electron to that to make hydrogen. Then remember, hydrogen is diatomic, so it's going to be H2. Therefore, I need 2 electrons and I need 2 hydrogen ions. 2 marks, 1 mark for this side, 1 mark for that side, and your equation is balanced. Okay, so good luck with completing the homework. Mark it as well, make any corrections, they should all be right by the end of it. Good luck.